In this tutorial, we will be discussing the differences between electrolytes and non-electrolytes. A strong electrolyte is something that disassociates 100% in water. What that really means is that it's breaking up into two parts, into a positive ion and a negative ion. So if we look down here at sodium chloride, when you put it in water, we have an Na plus and a Cl minus. And if it breaks up 100% of the time, it's going to be considered a strong electrolyte. Weak electrolytes do break up, but they don't break up as much. So notice how there's an arrow going the other direction. That's because it's going back into the HF format. So if you look over here at this picture, you still see HF bonded together. Whereas over here, there are no NaCls together. They're all separated. Non-electrolytes are those that don't dissolve in water at all. And so they are still considered the soluble version of that compound. So there is no plus or minus here. It's all just still the compound sucrose, which is sugar. So as a breakdown, we have strong electrolytes, weak electrolytes, and non-electrolytes. They're called electrolytes because whether or not they conduct electricity. Strong electrolytes conduct electricity, while non-electrolytes do not. Strong disassociates into the ions completely. Weak only does a little bit, while non doesn't do it at all. So if we look over here at CaCl2, we can break this up into its ions Ca2 plus and Cl minus. That 2 here for CaCl2 means that there's 2 chlorines. So make sure you bring that back up, because remember when we did the ionic compounds and we looked at the charges and we crisscrossed, and that 2 came from up here. That means we have 2 chlorines. That would give us the answer of C. We can do the same thing with this next one. We have K plus and PO4 3 minus. This 3 here came from the negative 3 here. So that means we actually have 3 K pluses, which gives us A. Which of the following reactions represent the dissociation of a strong electrolyte in water? So we're going to look for those positive and negative ions that have been broken up. This one was not broken up. The second one was not broken up. If you look at the third one, it was broken up into the ions of positive and negative, whereas the last one, once again, was not. So your answer here is C. Write the equation for the formation of a solution for the following: the dissociation of K2CrO4. We're going to put that in water and break that up. This is originally a solid. Now it's going to be in the aqueous solution. K plus, which is potassium, and there's 2 of them. And this is aqueous. Then CrO4 minus, 2 minus, once again aqueous. This time CrO4 is a polyatomic ion, so that 4 stays with it, and that's your final answer. Sugar, C12H22O11, dissolves in water. It doesn't dissociate in water. So if we have this compound and we put it in water, you're going to have the exact same compound, except now it's in aqueous format. Always be careful of the terminology they use: dissolves versus dissociates. Equivalence is something that they actually still use in nursing practices, so I want to make sure that we take a second to look at those. An equivalent is the amount of an electrolyte or an ion that provides 1 mole of an electrical charge, either positive or negative. The charge of the positive ions is always balanced by the negative, so the positive and the negative always have to be the same. The concentrations of electrolytes in intravenous fluids are expressed in milliequivalents per liter. For example, a solution containing 25 milliequivalents of sodium and 4 milliequivalents of potassium. 25 plus 4 gives us 29. And the positive and the negatives have to equal out. So if we have 29 positives, that means we're going to have 29 negatives. The laboratory tests for a patient include a blood calcium level of 8.8 milliequivalents per liter. If we are starting off with a half a liter of blood, we can convert this over to milliequivalents by 1 liter is 8.8 milliequivalents. However, when we look at moles of it, we have to get into regular equivalents, not milliequivalents. So for every 1,000 milliequivalents, there's 1 equivalent. Now, it's asking for moles. Calcium is a +2 charge. That means that there's 2 equivalents for every mole. So there's 2 equivalents in every 1 mole of calcium. So it would be 0.5 times 8.8 divided by 1,000 divided by 2. That comes out to be 0.0022 equivalents of calcium. Alright, so if we have 8.8 milliequivalents per liter of calcium, how many equivalents will we need of chlorine? So calcium is our +2, chlorine is our -1. So our positives coming from calcium, our minus is coming from chlorine. But no matter what, even though this is a +2 and this is a -1, the actual total equivalents have to be the same. So if we have 8.8 of calcium, that means we need 8.8 milliequivalents of chlorine. Also pay attention that it's asking about milliequivalents. They're not asking about moles. They're asking about the equivalency. Alright, so when we're looking at blood plasma, typical concentrations of electrolytes of blood plasma is right here. They have to have a total charge balance. The total number of positive charges equal the total number of negative charges, and it varies as the result of the nutritional electrolyte and fluids needs in the patient. So here we have 150 positives and 150 negatives. Here are some different IV bags. For the sodium chloride bag, just simply to replace fluids, we have 154 of each. If you have an issue with dehydration, we have 155, and it adds calcium in there too. So dependent on what the patient needs, you might have a different IV bag which has a different equivalency amount. Alright, so let's just quick overview. 1 mole of iron 3 plus, there are 3 equivalents in that because of that 3 plus. 2.5 moles of sulfate, for every 1 mole of sulfate, there's 2 equivalents. That brings us to 2.5 times 2, which gives us 5. An IV bottle contains sodium chloride. If the sodium is 34 milliequivalents, then the chlorine also must be 34. And that is the breakdown of electrolytes and non-electrolytes.